Hey class, Adam Ward here. We are going to go ahead and work through an example that we had at the end of our class focused on use of the energy equation. And so here we've got a problem where we're going to define points, 1 at the water surface, 2 in the thin-walled tubing that we're concerned about collapse of, and 3 at the free jet where that drains into the atmosphere. And so this problem comes in 2 parts. First part is to find the maximum value of H to prevent collapse of the pipe. And so this is a traditional Bernoulli equation problem. We can start by writing the Bernoulli equation between what I had labeled as points 1 and 2, that's the water surface and the thin-walled tubing. When we do so, we can simplify a couple of terms. So P1, V1, and Z2 can all be taken as 0. And when you do that, you're left with the following equation that I started filling in the constants for. So Z1 of 4 feet, P2, we know that critical pressure is minus 10 pounds per square inch. That translates to minus 1,440 pounds per square foot. Specific weight of water is on the bottom, and then plus V2 squared, we don't know V2 yet, over 2G. And when you go through that problem, you should find that V2 is 41.7 feet per second. Now, given information about point 2 and an understanding that whatever water is flowing past point 2 must also flow past point 3, we can apply the continuity equation. So A2V2 must equal A3V3. So what I'm writing out now is that equation numerically. So pi over 4 times the diameter squared, and notice I'm doing my unit conversion, 4 inches divided by 12 inches per foot right in there, times V2 equals pi over 4 times the radius at point 3, 6 inches, unit conversion to put that into feet squared over V3. And when I solve that, I get 18.5 feet per second of velocity at point 3. Now, finally, we can go back to Bernoulli again, and this time write Bernoulli between point 3 and 1 of the other points. I've elected to write Bernoulli from 1 to 3 because it simplifies the equation the most. So 3 terms drop out, and we can go ahead and fill in our Z1 term, Z3. So the first thing to the right of the equal sign is minus H, because it is a distance of H below what we've established as our datum. I'm plugging in my V3 squared over 2G, I get a height of about 1.3 feet. So we can have that discharge tube about 1.3 feet below the thin-walled section before we would actually collapse it, before we'd pass that critical threshold. So that was a review of the Bernoulli equation. Now let's go ahead and test your instincts. Let's see if we can conceptually explain this problem. And so this would be the appropriate time for you to go ahead and hit pause on the video. And given what you've done with the Bernoulli equation now, I want you to think critically. If we have a head loss of 0.75 feet upstream of the pipe, so say that happens where the tank starts flowing at the inlet, what will happen to H? Will you be able to make H larger or required to make it smaller in order to meet that same design criteria? So go ahead and pause here and think through it. And welcome back, everybody. Hopefully you've got an idea in mind. Let me walk you through my logic on this problem. So you can see in orange, what that head loss does is it functionally drops that upstream head to about 3.25 feet. Right? If immediately after that we have a head loss, that's equivalently what we've done. So our Z1 functionally goes down. And based on the previous problem, I know that if Z1 goes down, V2 is also going to go down. So that was the Bernoulli equation from 1 to 2. And if that velocity goes down, the pressure drop must not be as large. So if all we do is change the water surface, P2 actually goes up. So we gain some capacity there. That means we need to adjust H to drop P2. Okay, well, how are P2 and H related to one another? And so for this, I went ahead and wrote the Bernoulli equation between points 2 and 3. That relates the pressure at 2 to the elevation at point 3. When I look at this problem, there are two terms that zero out, my datum, Z2, and pressure at 3, which is a free jet. Now, I'm writing in purple here, V2 and V3 are functionally stuck. And what I mean by that is I can't really change the velocities to compensate in this problem, right? I'm not giving you the freedom to change pipe diameters. So you're kind of stuck with what you have. And so when I look at that, I think, well, how do you get P2 to go smaller? How can I make the left-hand side smaller? Well, I have to do so by making a corresponding change on the right-hand side. And so in order to do that, I need to have the quantity minus H get go down in magnitude, which means the value of H itself gets larger. So when I extend H, meaning make H bigger than it was before, I should get a corresponding increase in the pressure drop at point 2 and hit that design criteria again. Now, having done this problem once, I'll give you some space to do it on your own. An overview of the steps, you're going to apply the energy equation from 1 to 2 again, this time incorporating that head loss of 0.75 feet. So you'll get a new V2. Continuity equation, you'll get a new V3. Notice V3 has slowed down now, as has V2. Then we can apply the energy equation from 1 to 3, and I get a solution of height of 1.95 feet. And so what we've done by making this adjustment, or by incorporating that head loss, is we found that it changes the conditions under which we hit that critical point. For those of you who are looking for more of a challenge, what if head loss, instead of being some static value, is a function of discharge? So for example, what if head loss was equal to 2v squared over 2g? As we move through the semester, this is the strategy that we'll take for head loss as we add up losses due to friction and transitions from moving flow to quiescent flow or through pipe fittings as well. So go ahead and work yourselves through that thought exercise. If you're still looking for a challenge, how would your ability to solve this problem have changed if head loss weren't a defined quantity but had some direct feedback to velocities? Okay, I hope this helps, and I'll look forward to seeing you all back in class.